Hi everyone. So in this video we discuss a training strategy which is called training with teacher forcing, and this training strategy is typically used in networks with output to hidden recurrence, right? So the output of step 1 is connected to the hidden layer of step 2. The output of step T is connected to the hidden layer of step T+1. And what teacher forcing refers to is a very simple training strategy that instead of the output, it feeds when computing the loss of time step T, it feeds the target provided or the training label that is provided by from the training data set. So for example, if I have an input x of t minus 1 here, a time step t minus 1, it results in, it gets fed into a hidden layer h of t minus 1, results in an output o of t minus 1, and then I compute the loss function. Here we are assuming that the loss function is separable, meaning that you could decompose the loss function into a loss for every time step. Then we compute the loss function L of t minus 1 based on O of t minus 1 and Y of t minus 1. Y of t minus 1 is the target, the training target or the training label. Now this Y is what we feed into H of t at training time. At test time, we feed the output O of t minus 1 that results from basically the inference output from the network. Now, of course, and that's why actually that's why we assume the loss function is separable, because this strategy is mainly useful for speeding up the training, for parallelizing the training of the different time steps, so that you would not have to do back propagation through time, which is typically used when you have a hidden to hidden recurrence connection. And back propagation through time will be the topic of the next video. And here all I care about for you to know so far is basically you avoid the computation of forward propagation for all the time steps before you start back propagation through this separation between the different time steps. So I have access to the training labels before I start. I don't need to compute anything to get them. Right? So when I do this, when I feed the training target instead of the output of the neural network to the next time step, I could compute the forward and backward propagation, and I could compute the loss of the cost function. I could compute them for, let's say, the 100th time step before computing. I don't have to compute the first 99 in order to do that. Right? So that if I have access to efficient parallel computation, which is typically done through graphical processing units, I could parallelize the training of the different time steps. And this is particularly useful for long sequences. Now, another reason this is actually useful from a statistical standpoint, not just a computational standpoint, is that it basically implements or it captures the maximum likelihood principle. So if I take the logarithm of the conditional probability of y1 and y2, like the first two time steps only, given x1 and x2, this decomposes into the logarithm of the conditional probability of y1 given x1 and x2, plus the logarithm of the probability of y2 given y1, x1, and x2. Right? So if I remove this dependence of y1 and x2 here, right? And this basically is done by, or this reflects imposing a causality assumption that the output at a certain time step only depends on the current time step and the previous time steps, right? So if I impose this causality assumption, right, then basically what happens in training of teacher forcing would be identical to the maximum likelihood, because y1 would depend only on x1 and y2 would depend only on the previous inputs as well as y1, right? So and actually there is one more assumption for it to be identical to the maximum likelihood, because y2 here would depend on y1 and x2. Right? So we would assume that y1 is a sufficient statistic for predicting y2, right? Given x1. Meaning what? Meaning that all the relevant information about x1 that are useful for predicting y2 are summarized in y1. This is what the assumption is. So this is just for precision, right? So training with teacher forcing approaches maximum likelihood, but it's not exact. To be exact, you need the causality assumption, and you need the assumption that the training label at a given time step is actually a sufficient statistic or a sufficient summary of information about the inputs, the previous inputs, with respect to future prediction, right? So y1, the current target, is a sufficient statistic about x1 with respect to the prediction of y2. Sounds good? But even if these assumptions are not holding, we are approaching maximum likelihood, or we are coming closer to maximum likelihood when we do training with teacher forcing. So it's not only computationally efficient, but it actually is more faithful to the maximum likelihood principle. It could have statistical advantages. And in a very intuitive sense, you could think of it is that when I put the training target at every time step, it's like a correction step. Because the network output could deviate from reality, or could deviate from the ideal correct output. And this is actually the reason that the network output may deviate from the ideal output. This is the reason for a problematic issue that happens with training with teacher forcing in what is called open loop mode. And basically open loop means that I run the network in inference mode, right, for long sequences, right, without correction by training labels, without external correction. So the problem is that the errors could propagate. So if you have a small error in the network output, it will also affect the prediction of the next output. So you will have a larger error in the next output, which will affect the prediction of the further output. So you will have an even larger and larger errors. And for that, a curriculum learning approach. And curriculum learning, as the name suggests, means that it's a gradual, it's a learning approach where there is a gradual management strategy of the training data, right? This is what curriculum learning in general is referring to as an optimization strategy, is to give the network like an education curriculum, to give the network the training data set in order and in chunks, right? So here by curriculum learning, and it's in this paper right here, in 2015, the idea was that to make the network gradually depend on its own output instead of the training target. So you start by feeding the network the training targets like in normal teacher forcing, and then gradually you make it depend on its own output, so that when it operates in open loop mode, it can correct its own mistakes or deliver a reasonable performance in comparison to what would happen with pure teacher forcing. Sounds good? Thank you.